back to the channel. So today we will be solving this question called EQUATE XOR from the recent Codechef starters round, and it is pretty nice question and nice concepts involved. I will definitely recommend you to try this question on your own and try to come up with the solution, and it is worth a try. And if you are not able to solve, here's the solution. So equate XOR. And yes, today we will be learning one more concept called the disjoint set union. So that thing I have used to come up with the solution using the disjoint set union. So I will try to explain it to you. So here we go. Given an array A of n integers, consider an arbitrary non-negative integer. So given an array A of n integer, consider an arbitrary non-negative integer x. Okay, so initially score is 0, so we will sequentially perform the following operation for indices 1 2 so on up to n. For ith operation, if x is equal to the ith element of the array, then we will add x to the score and we won't update x. And if it is not equal to the ith index of a, then we will assign x is equal to x XOR a of I. Okay, so here this represents bitwise XOR operation. So I definitely assume that you know how XOR works. And note, when x matches ai during ith operation, you are not updating x. Yes. So we are tasked to print the maximum achievable score after doing n operations by choosing optimal initial value of integer x, and that too x is non-negative. So starting from 0 onwards, 0 1 and so on up to something. So we are tasked to print the maximum achievable score. So by choosing optimal x, we want to maximize the score. So let us take a look at the sample test case. Okay, I have copied it. So first of all, let us take a look at the sample test case. Here it is. Okay, let me take that. What is happening? Okay, anyways, better is this. That's better. And yeah, so one thing here, 2 is 1 0 in the binary representation, 1 is 0 1, 3 is 1 1, and this 3 is also 1 1. So one thing I can notice is that observation number 1. So if I choose the number which has the more number of bits than the larger number, so this is the larger number 3, and if I select 1 0 0, then there is no chance that I'm matching any of the elements of the array. Do you agree? Yes, you definitely do. Okay, so maximum number of bits, or you can say yes, that works actually. And if you select 4, there is no way you are matching the thing, so anything from the array. Okay, so we'll start by taking x is equal to 0. Okay, so I definitely recommend to try this x is equal to 0, x is equal to 1, x is equal to 2, and x is equal to 3. Try to operate through the array and check what values are we getting, and then you will notice for x is equal to 2, value that we got is 8, and which is the maximum of all the 4. Okay, so I will show you how we got 8. So if x is equal to 2, this is the first index, so it is equal to 2, so we will add 2 to the score. Okay, so we won't modify our x, then we'll go down here. So 2 is not equal to 1, then we will try to modify 2 with 2 XOR 1, right? So it will be basically 3. So we'll go forward. So now this is equal to 3. So we will add 3 to the score without modifying the x. We will jump one index further. We will also add this 3, okay, to our score. So 3 plus 3, 6 plus 2, 8. So that is the maximum achievable score. And that is what we are trying to achieve in this question, okay. And yes, so to solve this question, so what I can notice is that, so wait, so yes, I think it will be more efficient for you to understand the solution if I explain you how the disjoint set union works before the optimal solution, okay, before explaining the optimal solution, okay. So how disjoint set union works? So this is basically one of the most important data structures in the competitive programming. So basically, suppose there's a graph, okay, with 6 vertices. Don't be afraid of the word graph if you haven't heard it of or learned of some of the graphs. Uh, but yeah, it is basically the simple data structure to understand. So let us take a look. So there will be 3 procedures in the disjoint set union. Those 3 being make, find, and the union, okay. So what will make do? So one more thing, we will also take the help of parent array and size array, okay. Then what will this make do is that it will initialize parent of that node to itself. So when I call make of I, it will perform parent of I is equal to I himself or herself, whatever it is. I itself is the better word, okay. So and size of I to 1, okay. So basically it will instantiate the nodes, okay. So I will call make of I for suppose 6 nodes are there, so 1 2 3 4 5 6. I will call make of 1, make of 2, so on to make of 6. So basically parent and size arrays will also be initialized and nodes will be created, okay. And what this find of I does is that suppose find of I does is that it returns the parent of the node, okay. So after I've made make of I, then if I try to do find of 6, it will give me 6. If I do find of whatever it is 1, it will return me 1, okay. So that's basically the thing. And what will this union do? Okay, what will this union will do means is that, so these are the nodes. So let me copy that figure here. I cannot, okay, wait, maybe I can. Okay, I can. So here it is, and we are, oh, good, okay. So when I perform union of 1 comma 2, okay, when I perform union of 1 comma 2, okay. So okay, I was recollecting, okay. So union of 1 comma 2, if I call this function, so what will it basically do is that it will combine this 1 and 2 into single component, okay. It will create a virtual edge, you can say. By calling the union, you are creating a virtual edge, okay. So in the union, what we do is that we will find parent of find parent of 1, okay. Parent of 1, we will find parent of 2, okay. Then we will okay, there are two types of unions by size and union by rank. I'm performing union by size, so I will check size of P1. Okay, without loss of generality. Okay, wait. If I will check size of P1 and I will check size of P2. Okay. Size of P2 means, okay, size of P2 is such a thing that uh, what can I say? So it will basically return the number of nodes in that component. Okay, so basically suppose this is your component, so suppose this is the node 1, and if you call size of 1, it will return you 3. Okay, if you call size of, suppose this is one of the graphs. Okay, here it is 1. If you call size of 1, it will return you 5. So basically that is the number of nodes in the connected component. That's easy to follow. Okay. Okay, so that is basically what the size does. Okay, so I will compare the sizes of P1 and P2. So yes, when I compare sizes of P1 and P2, suppose without loss of generality, size of P1 is larger. Okay, so I will merge this size of P2 into size. I will merge the P2 into P1. What I mean by is that, so suppose I do union of 1 comma 2, I do union of 3 comma 4, suppose. So basically I sketch an virtual edge. I'll do union of 2 comma 5. Okay, so when I do union of 2 comma 5, so basically size of 5 is 1. Okay, yes, size of 5 is 1 and size of 2. Okay, size of 2, not size of 2 actually, size of parent of 2, size of parent of 2. So parent of 2 is 1. So how that parent is 1, I will explain in the path compression method. So there is something called the path compression. We will take a look at the code as well. So I will explain you the code. And size of 1 is basically 2, so size of 5 is less than size of 1. So I will draw an virtual edge here, so not an actual edge, so virtual edge here, and I will assign parent of 5 as 1. Okay, so I will assign parent of 5 as 1. Now I think you have got the enough idea for the make, union and the find functions. So let us take a look at the code. So make is basically the instantiating the nodes, parent and size are just the vectors, and we will come towards this. So basically just take a look at the union function. So void of union of A and B. So we will update A as find of A, so B as find of B. So basically finding the parents, and if A is not equal to B, then we will do these tasks. So why A is not equal to B, the condition is necessary. So basically if you perform union of A and A, doesn't make sense, right? So what is union of A and A? So that's why doesn't make sense means formally you don't do the union of the object with itself. Okay, so at least not in the disjoint set union. I don't know about the other education branches. So void of union of lla comma ll of b, and if the size of A is less than size of B, we will basically swap A and B. Without loss of generality, we take the size of A as size greater than size of B. Okay, and we will assign parent of B is equal to A. Basically, what we have seen in the explanation over the whiteboard. And size of A plus is equal to size of B. And yes, we also have to update the size of A, right? So it will be increased by the size of B, right? And what this path compression does is that, so okay, wait, so uh, don't forget to call the make for the every node. That is basically the most important part in the whole code, I would say. And yes, and to find the connected components, okay, I'll explain the connected components and the path compression thing hand in hand. Okay, so yes, here we are, another same graph. So suppose I call union of 1 comma 2, then union of 2 comma 4, and union of 4 3. Okay, so when I call union of 1 comma 2, okay, so when I call union of 1 comma 2, you'll notice on the basis of the code, parent of 2 is modified to parent of 1. Okay, and size of 1 will become 2, because it was initially 1 and then it will become 2 when I call union of 1 comma 2. Okay, let's do it step by step. Okay, union of 1 comma 2 will make these differences. Okay, and size of 2 will still remain 1. Okay, size of 2 will still remain to be 1. That is not of that significance for us. So next perform union of 2 comma 4. Okay, what is the parent parent of 2? Parent of 2 is 1. What is the parent of 4? Parent of 4 is 2. Okay, size of okay, parent of 4 is 2. Okay, so what I will do is that, so if parent of 4 is 2, if I don't do path compression, so what will happen is that, okay, sorry. So parent of 4 will be 4 itself. Parent of 4 will be 4 itself, not 2 or 1. And yes, then parent of 4 will be get updated as 1, because size of 4 is less than size of 1, right? Size of 1 is 2 and size of 4 is 1. Okay, and there will be this virtual edge. Okay, so now if I perform union of suppose, what you'll say, 5 comma 6, then the edge here, and size of 5 will become 2, and parent of 6 will become 5. Okay, and one more thing, if I do union of 3 comma 6, suppose, so parent of 3 will be 3 itself and parent of 6 will be 5. Okay, so here size of 5 will be 3 now, and parent of 3 will also be 5. So okay, now the part of counting the connected components. Okay, I've done union of 3 comma 5, right? So now time to connect, now the time to count the connected components. Okay, so suppose, okay, uh if I didn't do union of 3 comma 5, instead I did union of 3 comma 4. Okay, instead I did union of 3 comma 4. So to count the connected components, we will run a loop from I is equal to 1 to n, and if find of I is equal to I, so basically what that means is that the node is the parent of itself. Okay, when will that happen? Okay, so when I call the find of 1, it will give me 1. When I call find of 2, it will also give me 1. Okay, so if I call the find of 3, it should not give me 4, right? It shouldn't give me 4, it should give me 1. Okay, so basically that's the parent of the whole connected component, this whole connected component. Okay, let me change the color. This whole connected component, it should give me the parent of its whole connected component. So basically it will go here. It will ask the 4, are you the parent of whole connected component? 4 will say no. uh, then it will go to 2. It will ask, are you the parent of whole connected component? It will also say no. Then it will go to 1. Then it will say, are you the parent of whole connected component? Then 1 will say yes. Okay, so then find of 3 will return 1. So what we are doing here is that we are recursively checking the neighbors. Okay, not the actually the neighbors. So we are checking this step by step and going up till we find of I is equal to I. So if that is found, then we know that that thing is the parent of whole connected component. So that is basically the path compression. So when you try to find the parent of any node, uh, you just find the parent of its parent. Okay, you find the parent of its parent uh, until the parent of the node is itself. Okay, so I think that's the not so good explanation for path compression. I will try to make the independent video for disjoint set union. So anyways, let's focus now upon the actual problem that we want to solve. Okay, so yeah, so yes, we have took a look at the sample test case, and sample test cases were kind of weak, and I have designed a strong test case. So let us take a look at the logic. So suppose uh, my value x. Okay, so my value x will, suppose it becomes the a of some index for the first time on the index is equal to I1. Okay, so for the first time it becomes equal to the element of the array at index I1. So it becomes equal to the array element at the index I2 after the I1. So immediately after I1 it will become equal to the array element at I2, then at I3, and so on up till IR. Okay, so now I want you to focus at only these two indices, I1 and I2. So try to be patient, so video is getting long, but yeah, I think you are connected till here. Yes, so focus on these two indices. So what I can notice is that, suppose if x is equal to ai1, right, when we reach the index I1, okay, and x is equal to ai2 when we reach index I2, reach corresponding indices, right? Okay, so the elements which are between the index I1 and I2, so basically you do XOR with a of I1 plus 1, then you perform XOR of this thing with a of I1 plus 2, then you perform XOR with a of I1 plus 3, and so on. You keep performing XOR operations till a of, what you can say, a of I2 minus 1, right? So yes, what I can see is that this whole thing is equal to ai2. Do you agree with me? Yes, you definitely do, right? So this whole thing should be a of I2 because at a of I2 our x modified x, so this is basically whole modified x, this big thing. Okay, so this is basically the modified x. Okay, that looks like an egg. Okay, so this modified x will be a of I2, and if it is a of I2, okay, what I can notice is that suppose I do XOR operation from I1 to I2, I will get a 0. Will I? Yes, I definitely will, right? So basically, XOR of all these elements is A of I2, right? Is A of I2, and the I2th element is A of I2, and we know XOR of the element with itself is 0. Right, so A of I2 XOR A of I2, uh, XOR of AI, XOR of AI2 with the AI2 will be 0, right? Okay, and suppose another thing I will notice here is that so XOR of I1 to I2 is 0. So XOR of I1 to the last index n will be basically same as XOR of I2 plus 1 to n, isn't it? Yes, it definitely is. So basically, what I understand by this is that so I want to iterate, I want to iterate from n to 1. I want to iterate from n to 1 and uh, keep the track of keep the track of the suffix XOR. Okay, I want to keep the track of suffix XOR, and if the suffix XOR of suppose some index j, suffix XOR of some index j and suffix XOR of some index I, if they both are equal, listen carefully, this is the most important part of the solution. So if they are both important, okay, if they both are equal, then I know that if x was equal to the ai, then it will be equal to the a of j minus 1. Will it be? Yes, it definitely will. We have seen it here, right? So if XOR of I1 to n, so suffix XOR of I1 is equal to suffix XOR of, okay, look in the right corner. So suffix XOR of I2 plus 1, then these two are basically part of my sequence which will be contributing to my answer, to my score, right? So if suffix XOR of I and j are equal, then I and j minus 1 will be in the same will be in the, what you can say, will be in the same subsequence which will contribute towards the answer. Okay, so let us take a look at this sample test case. Okay, now sample I have made it. Okay, oh, sad. Let's take this whole thing right down here. Okay, so I want to, now I want to make the groups, make the groups of the indices, right? Okay, so index, suppose index 1 will have its own group, index 2 will have its own group, index 3 will have its own group. Not own group, suppose index 3 can also be in the group of 1, right? So index 4 can also be in the group of 1. So we will see. Okay, so how will I make the group of the indices? Disjoint set union. Okay, I will store the latest index where suffix XOR is equal to some value. Okay, so I will try to iterate from the backwards. Okay, suffix XOR is 3. So suppose I will create a map and I will store, so map of I, okay, not map of I, map of value will be the latest index where the suffix XOR is equal to value. Make sense? Okay. So let us dry run our algorithm. Okay. Let us still take this down. Okay, I cannot. Sorry. I will erase this. Okay. So try remembering the definitions. So yes. And one more thing, map of 0. Map of 0 will be n plus 1. So map of 0 will be 11. So this is basically the thing for if some group of the indices involves the last index. So I will explain what that means. So map of 0 is 11. Then map of 1, oh okay, map of 3 is 10 based on this thing. Map of 1 is 9. Map of 0 is 8. Okay, now listen. So map of 0 is 8 and map of 0 is also 11. Uh, Noticed something. So suffix XORs are equal. So basically my 8 and 10. So 8 and j minus 1. Listen, j minus 1. So my 8 and 10 will be in the same group. Okay, will be in the same group. Okay, so next. So okay, so we have made it till where? 8. So here, next. So map of 4 is going to be 7. Okay, then map of 2 is going to be 2. Okay, map of 2 is going to be 6. Sorry. Okay, then fifth. So map of 0 is already 8. So yes, time to do union. Union of 5th index and 7th. Remember j minus 1. Okay, and update map of 0 to 5. Yes, good to go. Now we are at 4th index. So map of 2 is already defined, 6. So time to do union. Where are we at 4th index? And 6 minus 1 is 5. And yes, don't forget to update map of 2. Map of 2 is going to be 4. Everything fine. Map of 1 is 9. Map of 3 is 10. Map of 0 is okay, 5. Okay. Let's erase this guy. Map of 0 is 5. Map of 0 is 5. Okay. And yes, proceed forward. So map of 4, where is it? Yes, define time to do the union. Map of 4 is 7, so 6 unioned with 3. And don't forget to update map of 4 to 3. Next index. Map of 1 is already predefined. Okay. So of 1 is predefined. So time to do the union 2 with 9 minus 1 and update map of 1 to 2, right? Now this index map of 2 is already defined, so time to do the union of unions are depicted in blue color. Okay, so time to do the union of 1 comma 3. Yes, and update map of 2 to 1. Did we go correct? So map of 1 is 2. Yes. Map of 2 is 1. Yes. Map of 4 is 3. Yes. Map of 3 is still 10. Yes, it is. Map of 0 is 5. Yes, we have done it correctly. And yes, so union of 1 comma 3 and 3 comma 6. So basically it will be 1 comma 3 comma 6. This is done. This is done. Then union of 2 comma 8 comma 10. Okay, so that's done, done and dusted. That's good. And 4 comma 5 comma 7. So these are the candidates for your answer. Okay, finally we have arrived at that point. So let us take a example of this 1 comma 3 comma 6. So this index, let me change the color. This index 1 comma 3 comma 6. Now at what initial value of x will you get this sequence? So uh, obviously x is equal to 3, right? So basically the first one, the first thing is also matching, right? So for x is equal to 3, so add 3 to your score, then XOR 3 with 5, so it will basically become the 6. And yes, we are matching with the third index, so 3 plus 6 plus, so here our x is 6. Okay, at this index our x is 6. Further, so 6 you want to XOR with 2. Okay, 6 XOR 2 is 6 XOR 2 is 4. So here your x will be 4. 4 again, 2 is again basically 6. So yes, we are matching our sixth index, which is 6. So yes, we have successfully unioned the things. I think that's pretty much the solution. Let's head towards the code, okay, to understand what's going on. And yes, and that's the line 5 to line 38 disjoint set union template, and n taking the input, making instantiating every node, and this is basically the process explained in the solution. So basically you start from n, go towards the 1 and do the thing. And yes, and this is also important part. So for every index I, you'll add its value to its parent only, right? So you'll add its value to its parent only, so union thing, right? And yes, maximizing the answer based on the previous answer and every element in the answer map, and finally outputting the answer. So I think code is pretty straightforward to follow if you have heard the solution completely well. And yes, I hope you enjoyed solving the question on your own and listening to the solution as well. Thank you for watching, and consider liking the video if you really understood the solution, and staying tuned, staying subscribed to the channel. And thank you for watching again. See you again. Surely.